In this module, we will examine how the uncertainty in radiochemical measurements is calculated. This module will cover the basics of determining uncertainty of radiochemical measurements. You will be able to define the terms accuracy, precision, standard uncertainty, and coverage factor as they apply to statistics. Identify measurement parameters that will follow the normal distribution. Calculate the counting uncertainty given the number of counts or the count rate and count time. Identify the various measurements that are made in radiochemical analyses that factor into the final combined uncertainty. Calculate a critical level, MDC, and Safe Drinking Water Act detection limit based on counting parameters and sample-specific parameters. The key concepts that will be emphasized in this module are: every measurement has an uncertainty associated with it that can either be calculated or estimated. The uncertainty due to radioactive measurements can be calculated knowing the number of counts and the count interval. The sample critical level is the determining factor for whether a sample has detectable activity, and the determination of detectability is based in part on the tolerable error rate that is selected. Whenever any kind of measurement is made, there is uncertainty of the measurement with respect to what the true value is. Suppose that a measurement is repeated by the same person, by a different person, using a different instrument, or using a different part of the same sample. For each of these 4 different instances, you would likely get a slightly different result. That's because any time a measurement is repeated, even by the same person using the same instrument on the same material, the distribution of the final measured values will vary in a manner that can be described probabilistically. For example, draw a line, then use a ruler to measure its length. Then give the ruler and the paper with the line to another person to make the same measurement. The estimate they make of the line length using that ruler will vary slightly from the original measurement that you made. The things that affect the difference in measurement are interpolation of the markings on the ruler, visual acuity of the observer, variation in the temperature of the room, etc. All measurements suffer from these types of variables, and others as well. These cause our measured values to differ slightly each time we make them. There are several terms used to describe the probabilistic distribution of results. These are the mean, the variance, standard deviation, and others. The key concept to remember is that no matter what the measurement is, there is an uncertainty associated with it that can be calculated or estimated. The figure on this slide is for a Gaussian distribution of results. Sometimes this is also referred to as the normal distribution, since the probabilities of measurements that represent the true value are distributed equally on both sides of the true value. The x-axis represents the range of possible measured values, and the y-axis represents the number of times a measured value will be observed. There are some important features to note about this type of distribution. First, the mean value is exactly in the middle of the distribution. In a true Gaussian distribution, the mean and the median, the middle value, will be the same. They will also have the highest probability of all possible values. In statistical parlance, the result that occurs most frequently is called the mode. Second, the equation for this distribution has an exponential function which causes the probability of a result occurring to decrease significantly as one gets farther away from the mean value in both directions. However, the curve never goes to 0. Third, we can divide the curve up into segments that represent certain fractions of the total area under the curve. The parameter sigma, called the standard deviation, is the measure of the width of the curve. It can be used to identify different portions of the total area under the curve. As shown on the figure, if we take the area under the curve that is encompassed by the mean value plus and minus 1.96 sigma, 95% of all results will normally fall into this range. So if the mean were 10 picocuries and sigma was 1.0 picocuries, then the range of values that would correspond to 95% of the possible measurements would be from 10 minus 1.96 picocuries to 10 plus 1.96 picocuries, or a range of 8.04 to 11.96 picocuries. The figure on this slide shows another type of probability distribution. This one is described by a linear relationship on each side of the mean value. This type of distribution is what might be assumed for use of a volumetric pipette. The terms and their definitions shown on this slide are commonly used in discussions of uncertainty measurements. One of the important concepts to remember is that when we perform an analysis, our measurement is a representative of all possible measurements that could be made. That is, our single measurement ends up representing the entire population. Even if we perform replicate analysis on a sample, it is still only a sample of the entire population. The mean of a series of measurements is simply the sum of all the individual values divided by the total number of measurements made. Traditionally, this parameter has been represented by an x with a bar over it, or x bar. In more statistical parlance, it is referred to as q bar. The equation to determine the experimental standard deviation is shown on the slide. The term variance is the square of the standard deviation. Variances of different measurements may be added directly, whereas the standard deviation is not. We will perform some calculations later in this module that demonstrate the use of variance to estimate the total uncertainty. The definition of uncertainty according to the Guide to Uncertainty of Measurements is quoted on this slide. Since every measurement has an associated uncertainty, any result must be reported either with a calculated or an estimated uncertainty. Always. Reporting the uncertainty with the measurement allows the data user to have a certain level of confidence of how closely the value reported represents the true value. For example, suppose you to get a report for uranium in drinking water of 25 picocuries per liter. Without the reported uncertainty, you have no idea what this value represents with regards to the accuracy of the measurement made. Values should be reported with their uncertainty as a multiple of the standard deviation. When one standard deviation is used, this is referred to as the standard uncertainty. It is also called the 1 sigma uncertainty. So let's go back to our example and say the value is 25 plus or minus 350 picocuries per liter, where we have reported the 1 sigma uncertainty. The meaning of this value is much clearer. This was not a value that can tell us how close to the drinking water limit of 20 picocuries per liter the sample actually is. In contrast, if the reported result was 25 plus or minus 1.2 picocuries per liter at 1 sigma uncertainty, we could have a good deal of confidence that this sample has exceeded the 20 picocuries per liter limit. In order to calculate the combined standard uncertainty, we need to establish what mathematical model is being used. The output estimate is the result of combining several different measured parameters to yield a final result. Each measured parameter will have an uncertainty associated with it. Let's use an example of a measured number of sample counts and subtract the background to get the net counts. Each measurement of counts has an uncertainty associated with it. The net counts are the output parameter, and it is easy to see that the sample minus background equals net counts. However, how do the uncertainties of each of the measurements combine? The method of calculating a combined uncertainty has a formula just as we had a simple formula to calculate the output estimate. The combined standard uncertainty is calculated by using mathematical formulas. This process is called the propagation of uncertainty. We will not discuss how the mathematical formulas are derived. However, we will discuss how the formulas are used for many of the radiochemical methods to calculate the combined standard uncertainty. For more details on uncertainty and propagation of uncertainty, see Chapter 19 of MARLAP. It turns out that similar mathematical functions will have similar methods of combining uncertainties. Thus, the mathematical functions of addition and subtraction have the same formula for combining uncertainties. Multiplication and division are similar to each other, but different from addition and subtraction. Therefore, multiplication and division have a separate formula. As shown on this slide, when we add or subtract two measurement values, their uncertainties are combined as the square root of the sum of the individual uncertainties squared. This is referred to mathematically as being combined in quadrature. The example shown here combines two measurement values, 15 and 10. If the uncertainty for the measurement 15 is 1.5, and the uncertainty for the measurement of 10 is 2, the final value will be 25 plus or minus 2.5, where the value of 2.5 is one combined standard uncertainty. In a previous slide, we identified that the functions of addition and subtraction had the same technique of combining uncertainties. So in the example on the previous slide, if our output estimate was based on subtraction rather than addition, the combined standard uncertainty would still have been 2.5. The area on this slide, shaded in blue, summarizes these two different functions and the associated uncertainty for each. The relative combined uncertainty for each measurement is different. The relative combined uncertainty takes the combined uncertainty and divides it by the final output estimate. If we do this for the two separate functions of addition and subtraction for the examples shown, for the addition function, the relative combined uncertainty is 10%, but for subtraction, it is 50%. Relative uncertainty is a measure of analytical precision. Whenever possible, we would like to have a low percentage for this value. The concept of relative combined standard uncertainty shown here identifies how the overall method of computation of the output estimate affects the relative combined standard uncertainty and emphasizes that each uncertainty measurement can have a significant effect on the analytical precision. Given the formula for the output estimate shown for Y, the method of calculating the combined standard uncertainties is shown on the next line. This is the general form for the combined standard uncertainty that will be used in most radiochemical analyses. This format divides the squares of the uncertainties by the squares of their individual output estimates and then combines them in quadrature. Note that the same form is used for both multiplication and division. Radiochemical analytical results have many factors that are used to determine the output estimate. Listed on this slide are some of the input parameters that are used to get the final result. Notice that published values for constants is one of the categories. This means things like half-life or decay abundance factor contribute to uncertainty. One might initially think that these are constants and so they don't have any uncertainty associated with them. Keep in mind, however, that any constant is determined based on certain measurements. Thus, there is uncertainty associated with it as well. Keep each of these parameters in mind as we progress through the rest of this module. The tables on this slide and the next one identify the relative standard uncertainty associated with each type of input parameter used in the determination of a radioactivity concentration. Most analysts working with environmental samples tacitly assume that all of the uncertainty is due to the count measurement, since it is usually so close to background. Two of the most often ignored uncertainties that can contribute appreciably are the measurement of the radiochemical yield and the effect of attenuation, particularly for gas proportional counting analysis. Measurements made with traditional analytical instrumentation usually fall into the realm of Gaussian statistics with respect to the uncertainty of the measurement. This is because there is an equal probability of a measured value falling on either side of the true mean value. This is not the case with radiochemical counting at low levels. Radioactive decay, and consequently the number of counts observed, follows a different probability distribution called the Poisson probability distribution. It can be shown that for this distribution, the standard uncertainty of the observed counts is simply the square root of those counts. Simply stated, for an individual count, the standard uncertainty is the square root of the number of counts. The determination of radiochemical activity concentration in a sample will always require a sample count and a background count. We start here determining the uncertainty of a single counting event. Looking at the example calculation on the right, we observe 169 counts. The estimated uncertainty associated with this single measurement is 13 counts. It is important to realize that even though we are talking the square root of the counts, the final result is still in units of counts. The relative standard uncertainty for this single measurement is 7.7%. If you think back to one of the very first lessons where we discussed what radioactivity was, you'll recall that radioactive decay, leading to counts, are spontaneous and random. You'll also recall that the longer the observation period is, the greater will be the number of decays that will be observed. As we saw in the previous slide, the uncertainty is estimated by the square root of the counts. Putting all these concepts together, we can estimate the count rate uncertainty using the equations identified on this slide. Remember that the count rate R is equal to the number of counts N divided by the time. For the example shown, if we record 169 counts in 100 minutes, we get a count rate of 1.69 counts per minute with a standard uncertainty of 0.13 counts per minute. In the example shown here, the count rate calculated is the same for each measurement. However, which of these will yield a lower relative uncertainty? Try your hand at this calculation and then proceed to the next slide. For the two results, we get uncertainties of 1 count per second for the longer counting interval versus 10 counts per second for the shorter counting interval. Thus, the longer count interval provides a lower relative standard uncertainty even though the actual count rates are the same. Whenever we make a measurement of radioactivity, we must take into account the instrument background. Thus, the net counts are the sample gross counts minus the instrument background counts. Here, the concept of quadrature will be used to estimate the standard uncertainty for the net count rate. The sample count rate is 100 plus or minus 2 counts per second, and the instrument background is 10 plus or minus 1.5 counts per second. What is the result with its combined standard uncertainty? Again, try your hand at that calculation before proceeding to the next slide. The result is the net sample count rate with its combined standard uncertainty is 90 plus or minus 2.5 counts per second. Always report your analytical result with a stated uncertainty. The Safe Drinking Water Act has values for maximum contaminant levels that are used to determine if the water system may be acceptable for drinking water purposes. The Safe Drinking Water Act also requires that if a sample does not have detectable activity, that a lower detection level must be achieved for that sample. This lower value is the required detection limit. How do we know if we can achieve these values? This is discussed on the next slides. The verbiage that describes how the detection limit is determined is excerpted here from 40 CFR 141.25. This definition is based on the uncertainty of counting and nothing else. However, an equation that shows us how to calculate this is not provided in the CFR. The words in the CFR tell us that the 95% confidence level is used to determine how large the uncertainty can be with regards to the actual measured value. As stated here, if a detection limit is defined as 3 picocuries per liter, its associated uncertainty at that concentration must be 3 picocuries per liter or less at the 95% confidence level. This means that 1.96 times the standard uncertainty would be equal to 3 picocuries per liter. The two equations that are used to perform the calculation to determine if the detection limit has been achieved are shown here. The actual equation to be used is shown on the next slide. Although this equation appears formidable, it really uses parameters that we set or measure. This equation should be used to determine if each sample meets the specific detection limit set forth in 40 CFR 141.25. Shown here are example parameters that are used to calculate the sample activity. You should review the data in this slide and then use the equations from the previous slides to verify the net sample activity concentration plus its standard uncertainty, and also that the required detection limit has been achieved. The combined standard uncertainty for determining an activity concentration in a sample uses an equation that has all 4 mathematical functions in it, and as such will require the formulas shown here. The equation used for determining the gross alpha activity in a sample is shown here. We are going to use the general formula for uncertainty and perform a combined uncertainty calculation for this analysis. We have provided here some basic information for determining the gross alpha activity in a sample. The uncertainties for some of the measurements have been provided. The uncertainty for the counts and the combined standard uncertainty is to be calculated by you. Usually, the uncertainty associated with the counting interval can be considered as an insignificant contributor to the combined uncertainty. The first part of the calculation is to determine the net sample activity. This is needed to calculate the combined standard uncertainty. Show yourself that you can get this value of 87.44 picocuries per liter for the gross alpha concentration. Using the general formula for the combined standard uncertainty previously shown, we will have three components that we will use: the count rate uncertainty, the efficiency uncertainty, and the sample volume measurement uncertainty. In order to calculate the uncertainty of the count rate, we need to calculate the count rate itself and its associated uncertainty. The net count rate is 3.3 counts per minute per the data provided. Since we don't need the count rate uncertainty all by itself, but the variance, we have shown here the value for the square of the count rate uncertainty as 0.037 counts per minute. Taking these values into the equation for the relative combined uncertainty, we then add in the relative uncertainties for the efficiency and the volume measurement. Note that in this instance, the counting uncertainty accounts for about 25% of the total uncertainty, and the efficiency is the largest contributor to the uncertainty. If you recall the shape of the Gaussian distribution, the ends were asymptotic to the x-axis. What that meant was that as you get farther away from the mean value, you get less and less likely to make a measurement that is representative of that distribution of values. When we make radioactivity measurements and expect zero as the result of that measurement, it also means that there is the probability of getting high values that could be considered true activity. We need to determine at what point above the mean concentration we say that we have true activity in the sample that is not zero. What is the confidence level that we want to achieve to do this? This level of confidence is also referred to as the tolerable error rate. Typically, a value of 5% is chosen. The result of this process sets our limit for a type 1 error. A type 1 error is one where we state that the sample has positive activity, that is, non-zero activity, when in fact it has zero activity. The point that we set for the type 1 error is referred to as the critical level. The graph on the right side of this slide shows a Gaussian distribution with the mean value at 0. The critical value is set so that 95% of the time an analytical value will be considered part of the background. The critical value is equal to 0 plus a constant times the standard uncertainty of the distribution. The constant for a 5% tolerable error rate is equal to 1.645. Note that this value is different from the 1.96 value used for a 95% confidence interval because the type 1 error rate only uses one side of the Gaussian distribution. In order to calculate where the critical level is, we need to calculate the standard uncertainty for the analysis. Keep in mind that if we are using this to determine the critical level for a sample, two measurements are required, one for the sample and one for the instrument background. The determination of the sigma 0 value using a single blank count measurement can be best approximated by the term under the radical sign in the second equation. When the sample and blank count times are the same, this equation simplifies to the equation shown on the right. For a detailed description of this derivation, go to MARLAP Chapter 20, Section 20.2. The factors to be used in the determination of the gross alpha or gross beta concentration are listed on this slide. The critical level concentration then becomes the value determined by the equation shown when an error rate of 5% has been selected for a type 1 error. The critical level so determined is now sample specific, that is, a posteriori, after the measurement. The data for an individual sample is shown in the blue area of this slide. The formula from the previous slide is applied to calculate the sample-specific critical level. Thus, using this single count for background and the sample-specific information, if the calculated value for activity exceeds 1.48 picocuries per liter, the sample has detectable activity at a 5% error rate. The term minimal detectable concentration, or MDC, is a different concept from the critical level. The critical level deals with only a type 1 error at a small acceptable error rate. The MDC determines the chances for the sample both being greater than the critical level for the blank and less than the critical level for the blank. Thus, the MDC concept includes both type 1 and type 2 errors. MDC calculations are usually a priori, that is, a calculation made before the measurement, and the MDC is based on nominal values for the parameters used for counting the sample. An MDC value is theoretical and not sample-specific. Therefore, the MDC should not be used for the purposes of radionuclide detectability. Another way of stating the MDC is shown on this slide. Note that the type 1 error rate is 95% and the type 2 error rate is 5%. The MDC looks at the detectability issue in a different format than the critical level. The two curves on this slide show the distributions for the radionuclide-free sample, or the blank, and for the sample that contains radioactivity at the minimum detectable concentration. Remember that the critical level concentration is based on the blank measurement and an assumed small type 1 error rate. The MDC is trying to determine simultaneously that there is a small probability that the sample count belongs to the background distribution for no radioactivity, the curve on the left, and that there is a large probability that the sample contains detectable radioactivity, the curve on the right. The two curves for the results of the infinite sample distribution cross at the critical level for the radionuclide-free sample distribution. The concentration which represents the MDC is the mean of the sample distribution that is possible. Thus, 50% of all samples that are at the MDC will actually measure to be less than the MDC. This does not mean that there is no detectable activity. In order to adequately address how to determine an MDC, we need to first look at the previous two graphs and assess how to get to the MDC value on the curve on the right. The signal response is the x-axis. If we use the critical level signal as the starting point, we need only to add the type 2 error rate times the standard uncertainty of the true mean to get the signal response that corresponds to the MDC. When we make the assumption used for the MDC calculation and apply it to the minimum detectable signal, the values for the tolerable error rates for 95% and 5% are the same. The value is 1.645. The equation from the previous slide can be simplified to the equation shown here. Keep in mind that the value for sigma 0 for a single background measurement is the same as shown in slide 38. For the exact development of these equations, refer to Chapter 20 of MARLAP. The data shown on this slide is the same as that we used for the Safe Drinking Water Act calculation of the required detection limit. The definitions of these detection limits are very different. Thus, we should expect different results. The final value of 4.06 picocuries per liter using the MDC equation is greater than the value of 2.4 picocuries per liter determined using the Safe Drinking Water Act calculation. When different equations for detection capability are used, different results will be obtained. In the case of the SDWA, the EPA defines how detectability is determined. That is a legal reporting requirement, and no other method should be used. We have introduced a great number of statistical concepts in this module that relate to uncertainty and measurements. This is an introductory module to these topics, and the student should review other texts and literature, such as MARLAP, to get a more thorough understanding of these topics, as well as more advanced concepts. Review the objectives listed here, and review this module to ensure that you have a basic understanding of each of these objectives.